Good morning, everyone. Welcome to the last session of this geometry workshop. Let's start. So, today we have Dr. David Woodruff with us. He is a professor at CMU and he received his bachelor's, master's, and PhD degree from MIT. And his research interests are in sketching algorithm, streaming algorithm, machine learning. He has received many awards, including Prisberg Award and IBM Master Inventor Award. Welcome, Professor David.
Thank you. Thank you for the introduction. Thanks for the invitation and thanks for coming. So today I'm going to talk about a strong separation for adversarially robust L0 estimation for linear sketches. I'll explain what each of these terms means. This is joint work with Alina Gribeluk, Honghao Lin, Huacheng Yu, and Samson Zhou. So I'm going to be talking about the streaming model. As input, we have elements of an underlying data set S, which arrive sequentially. And we want to approximate some function on this data stream. And our goal is to use space or memory, which is sublinear in the size m of the input stream S. And we're going to focus on the distinct elements problem, which is a classic problem, has applications to geometry. Various streaming geometric problems use it. And the problem is as follows. So given a set of n elements from the universe 1 through n, let fi be the frequency of element I. That is, how many times item I occurs. Then we let capital F sub 0 be the zeroth frequency moment. What that means is the number of distinct elements. That is, it's the number of items I in the universe for which the frequency f of I is not equal to 0. Okay, and our goal is given a set S of m elements, so a stream being given to us sequentially one element at a time, from a universe of size n, and then accuracy parameter epsilon to output a 1 plus epsilon approximation to f0. Okay. Now, a special case of this is when you have so-called insertion-only streams. So you think of having an underlying frequency vector x, which each coordinate, the ith coordinate xi represents fi. How many times did the element I occur in the stream? And in an insertion-only stream, you can only increase these coordinate values. Okay, you can't delete items that have previously appeared in the stream. So, for example, this could be your stream, and you see that you're just seeing new items. At the end of the stream, this vector x has 3 1s, so the first coordinate is 3. And it has 1, 2, so the second coordinate is 1, and so on. Okay, so it's indicating the frequencies of the items. There are 4 distinct elements in total out of 5 possible here. Okay, so there's a long line of work on streaming algorithms for estimating the number of distinct elements. Sometimes it's called F0, sometimes it's called L0. All these algorithms give 1 plus epsilon approximations to this quantity. So Flageolet-Martin gives an algorithm with order log n bits, assuming constant epsilon and a random oracle model. And this was successfully improved in a number of works. And the optimal bound is known. It's 1 over epsilon squared plus log n bits. Okay, so this is both an upper and a lower bound for estimating the number of distinct elements up to a 1 plus epsilon multiplicative factor. And if you just wanted to estimate the number of distinct elements up to an additive epsilon times n, there's a very simple algorithm. So just uniformly sample order 1 over epsilon squared universe items and see, maintain for each of those samples whether or not the item actually occurred in the stream or not. Okay? And with some more sophistication, you can actually get 1 plus epsilon relative error. Okay, so that's all fine. This talk is about adversarially robust streaming. And in this setting, the elements of an underlying data set S, the stream, arrive again sequentially, but now they arrive adversarially. Okay, so here's, again, I'll describe what that means. Again, your goal is to approximate a given function, and you want to use sublinear space. Now, what does adversarially mean? So think of some adversary, potentially, as generating the stream and giving it to the streaming algorithm. So it generates the number 1, and the streaming algorithm says, okay, there's one distinct element so far. It generates the number 4, then the streaming, it gets to see the algorithm's output. So, let me go back. So it sees that the algorithm output 1, and then it decides, based on that, what its next streaming input is going to be. And it says, okay, I'm going to give you the number 4. It sees that the streaming algorithm output 2 distinct elements, so the streaming algorithm is still correct. And it says, okay, I'm going to give you the number 2 now. Streaming algorithm got it correct again. I'm going to give you the number 1 now. And the streaming algorithm failed. It said there were 4 distinct elements, but actually there were only 3 distinct elements. Okay, so the goal of the adversary is, based on the responses of the streaming algorithm that it's seen so far, to try to come up with a new input, a next streaming element, which will make the streaming algorithm fail. Okay, and the goal of the streaming algorithm is to be robust against such adversaries. Yeah?
So does it get to see the algorithm's data structures, or only its output?
So that's a great question. So there are 2 models here. We're going to focus on what's called the black box model, where it only sees the output of the streaming algorithm. There's also the white box model, which is studied, where you get to see the internal state of the streaming algorithm. Now, if you can see everything, including all of the randomness, then it actually does reduce to just having deterministic algorithms. But there are other intermediate models where the algorithm gets some fresh randomness that's at each step that's unknown to the adversary, and this helps you get non-trivial bounds for that model as well. Yeah.
Any randomized strategy, even if with the black box model, it keeps observing what the algorithm is doing, it can actually guess, right, what it is, how it is doing.
Yeah, I mean, so it only gets to see the output, but the output, is a function of the randomness, and so it's slowly learning some stuff about the randomness. And the goal of the streaming algorithm is maybe to try to hide that information about the randomness. Yeah. Yeah.
Sorry, I failed to understand. So how is this model different from the results you showed in the last slide?
So those were all in the non-robust setting. So in the non-robust setting, the stream is fixed in advance.
I see.
And then you just ask to be corrected each time. But here, you get to choose the next stream element based on the previous answers. Any other questions? Okay, good. Yeah, so got it wrong. So adversarially robust means future queries may depend on previous queries. So the motivation, and the way I've been describing it is with an adversary. But so there are certainly adversarial situations, but I want to also argue that in common situations, the next stream items might depend on previous outputs. For example, you might have a stream of stock market data where you're making predictions based on it, and these outputs are so maybe you purchase some stock based on your predictions, and these therefore influence the market and cause future stream updates to depend on your past choices. Or sort of more obviously, maybe in optimization, you're minimizing some function, and so at each step you're querying some sketch based on what the sketch previously output for the optimization. Okay, so there's sort of naturally occurring cases where future queries depend on past queries, even non-adversarial settings. Okay, what's known about the robust case? So if you just have this model where you're only inserting stream items, and you want a 1 plus epsilon approximation, the first work with Ben and Eliezer et al. Showed that you can get 1 over epsilon cubed memory up to polylogarithmic factors in n. It used 2 techniques, sketch switching and computation paths, which both gave this bound. This was improved by Hasidim et al. To 1 over epsilon to 2.5 using differential privacy, which was a very nice connection that's been used for many other problems in this area. Intuitively, you're trying to keep your randomness private here. And using another technique called difference estimators, this was improved to the optimal 1 over epsilon squared dependence on epsilon in work with Joe. Okay, so these are actually nearly tight up to polylog n factors for insertion-only streams and adversarial robustness. What about insertion-deletion streams? Okay, so these are very important in geometric applications where you can insert and delete points. So here, each update ut, it specifies both the coordinate in the universe 1 through n together with a change in value, which can be positive or negative. Okay, so this delta t might say, you know, add 1 copy of coordinate at or subtract 1 copy of coordinate at. So these are called insertion deletion streams. For simplicity, let's indeed assume that delta t, the change, is minus 1 or 1. And in the robust setting, as we know, each update ut can be chosen adversarially. What is known in this setting? So there is a non-trivial bound of Ben Eliezer et al., which shows you can get m to the 1/3 memory. Here, m is the actual length of the stream. Okay, so this is not a great bound if m is large. You know, in the data stream model, you typically have a very long stream. So nothing is known for constant factor approximation in space that is polynomial in the universe size, much less polylogarithmic in the universe size.
So
Yeah.
everything so far is 1 pass, right?
Yeah, so this is all for 1 pass, yeah. It's a good question, exactly what multiple passes means in the adversarially robust setting. Yeah. Okay. Yeah, so we're going to focus on a type of streaming algorithm called a sketching algorithm, a linear sketch. This type of algorithm, what it does is it chooses a linear map A from some distribution, which this linear map A is a matrix. It's a wide, thin matrix. Okay, so it has a small number of rows and a large number of columns. So A times x is compressing this input vector x, which is undergoing additive updates to its coordinates. Okay, so this is a frequency vector, and we're compressing it with our sketching matrix A. Okay, so at the end of the stream, but by the way, since this is a linear map and A doesn't depend on x, it's very easy to update this sketch when you see updates to the coordinates of x. Okay? And at the end of the stream, the algorithm outputs some function f of A times x. Okay, the function can be arbitrary. Okay, so in fact, all insertion and deletion streaming algorithms for sufficiently long streams are in the insertion. Yeah. So for sufficiently long streams, all insertion and deletion streaming algorithms are in fact linear sketches. Okay. We don't know how to do anything other than linear sketches. And there's some general work we have with Lee and I et al., which shows that for very, very long streams, the optimal algorithm might as well be a linear sketch. Okay. There is a technical condition there, but all known streaming algorithms for long enough streams to get the optimal bound are in fact, the best known bound are in fact linear sketches. Okay, so this is the motivation for studying this kind of algorithm. Okay. So it's known in some cases that linear sketches are not robust to adversarial attacks. So in work with Hart, we showed that for certain problems, a linear sketch needs to use linear in x in the dimension of x space. Okay, so omega n space. And here's the basic idea how to attack linear sketches. This was for the problem of estimating the, say, Euclidean norm of the vector x. In fact, it works for any LP norm. So the idea is the attacker is going to try to learn this sketching matrix by making certain queries, and after it learns it sufficiently well, it can query a vector which is in the kernel of this matrix A. Okay, so remember this matrix A is wide and thin, so it has a large kernel. If I query something in the kernel of this matrix, it sees the 0 vector. Okay, so if it's going to get a multiplicative approximation, it has to output 0, but in fact you queried it with a non-zero vector. Okay, so it's trying to learn the kernel. How does it do that? It's an iterative process. So it starts with, let's call subspace V1 is the empty space. It knows nothing about the sketchy matrix. And it queries a bunch of vectors. I'll describe a little bit more on the next slide, but a bunch of random Gaussian vectors of different variances. And it tries to find vectors that are slightly more correlated with A than random. Okay, so at the very beginning, V1 is the empty set, is trying to find V2. And so it's trying to find vectors which are slightly more correlated with the row span of A than just random vectors. Okay? And by observing the outputs, it can do this. I won't describe exactly how, but that's what it's doing in each step. It's doing some kind of correlation finding. Like you can imagine that if I query a random vector to a sketch, a random Gaussian vector, then there's some output distribution on the vector the sketch sees. But you can imagine that if I'm slightly more correlated with the row span than random, then it's likely that this output vector might have slightly larger norm than that if I weren't correlated. Okay, and that slightly larger norm might then influence the actual function applied to that vector for the estimator. Okay, now there's a lot going on there in the sense that the function output doesn't need to be monotonic in the norm and so on, but there's a way of doing this. And so, it makes a bunch of queries in each round, and it looks for ones that are more correlated than random, and it comes up with another vector v, and it adjoins it to the row span of A that it's learned so far. So it goes from vi minus 1 to vi, and so it slowly does that until it learns the row span of A very well. Okay. The attack randomly generates Gaussian vectors in each iteration, and I want to emphasize a key point that the analysis crucially uses rotational invariance of Gaussians in the attack. Yeah.
When you say query vectors, you mean change coordinates?
Yeah. How does that correspond to a stream? You can think of creating an underlying x vector in the stream, querying the answer, and then deleting it, resetting it to 0, and making another vector x in the stream. Okay, so each such vector is a query vector. And so in each step, the attack is going to generate Gaussian vectors. At the beginning, they're isotropic Gaussians, so identity covariance times some scalar. And throughout the attack, these Gaussian vectors are orthogonal to what you've learned so far. But the details aren't so important. I want to just mention that this attack critically uses rotational invariance of Gaussians. And so the attack actually only works on real valued inputs, okay, which is the main difficulty. Okay, in a stream, you don't actually have real valued inputs. If you had real valued inputs, it's difficult to formally say what the memory is, right? What's the memory to store a real number? Okay, so we always think of streams as having discrete inputs, which is problematic here because if we try to maybe round the Gaussians, then it's not so clear that we can argue that we're making progress, okay? Because the analysis fundamentally needs this rotational invariance of these of the Gaussians, and once you round them, they're no longer rotationally invariant. Maybe there's some information in the lower order bits. And also critically, this attack only works for LP norm estimation for p greater than 0, whereas this talk is all about L0 estimation, or F0. Okay, so if I scale a vector by some scalar c, all the LP norms go up by a factor of c if p is greater than 0. If p equals 0, the L0 norm doesn't change, right? So there are fundamental reasons this previous attack doesn't work here. Our contribution is we show that there is some fixed constant epsilon. It's a lower bound, so that any linear sketch which gives this constant approximation to the number of distinct elements on an adversarial insertion deletion stream, using a number r of rows in the sketch, which is not too close to n, so say at most n to the 0.1, can be broken with r to the 8th queries. Okay, so this is an attack that can break any such sketch. So any streaming algorithm in this adversarially robust model. Okay. So I'm going to go over the intuition of this attack. Are there any questions about the result? Okay. Okay, so we're going to look at what I call the gap L0 norm problem. Let alpha and beta be fixed constants. We want to look at a decision problem. Distinguish the case where the number of distinct elements in the stream is at most alpha times n, or it's at least beta times n. It's a decision problem. Alpha and beta are constants. Alpha is less than beta. Okay, so if we have a good streaming algorithm, we should be able to solve this decision problem. When neither case holds, the algorithm is allowed to output arbitrarily. Yeah, so a good streaming algorithm can solve this gap problem. Okay, so a motivating question that got us started is the following. We can think of some coordinates of the input vector as being significant. Okay, so there are n coordinates in the vector x, n possible universe items. And we say a coordinate is significant if it's learned well by the sketching matrix A. Okay? Now what does that mean though? Like what does learned well mean? Well, here's an example. Okay, so suppose your vector x is 0, 1, 0, 1, 0, 0, 0. And here's your sketching matrix A, which has 2 rows. And you're computing A times x here. And if you look at the first coordinate of A times x, well, it's just the fourth coordinate of x, right? Because it just has a single 1 in the fourth position. Okay, so if I look at A1, the first coordinate of A times x, it actually tells me what x sub 4 is. Okay, so we should think of 4 here as being a significant coordinate. But maybe, yeah. So that's one natural notion of significance. And there are algorithms that we talked about. If I just sample a subset of streaming items, of universe items, and store whether or not they occur in the stream, that actually has this form, right? Where I just have a bunch of standard unit vectors as my sketch. Okay, so the outline of the attack is the adversary wants to gradually learn the sketching matrix. And the strategy is it's going to iteratively identify the significant coordinates. And as it identifies them, it's going to set them to 0 in all future queries. And after, and we have to show that there actually is an after, that this terminates. After we have learned all significant coordinates, the query algorithm must then rely on the other coordinates, for which the sketch AX only has small information. It's not very helpful. Okay, but all this needs to be made precise, okay? So let's consider the extreme example I talked about, where the sketch A times x is just a subset S of R coordinates of x. Okay, unknown to the adversary. Okay, so this is just sampling a subset. So the attack, in this case, boils down to the following. The first step from the previous slide reduces to identifying S, this sampled set of coordinates. After it does that, it places 0 in S and non-zeros elsewhere. Okay, so the streaming algorithm can't tell, it's just going to see zeros in its sample. It can't tell if elsewhere is all zeros or elsewhere is, say, all non-zeros. But since the size R of S is small, it means the L0 norm differs by at least a constant factor in one case versus the other, and so it's going to get the wrong answer. Okay, how can we solve this special case? So we're going to use what's called fingerprinting. So here's what's called the interactive fingerprinting code problem. There's an algorithm P which is selecting a subset S of the n universe items. And this subset is unknown to what's called a fingerprinting code, F. And F is trying to identify S, you can think of it as the adversary, by making adaptive binary queries. Okay, in the T step, it queries binary vector CT. And there is some restriction on the algorithm P, some correctness requirement, but it's a very, very basic requirement. P must answer consistently with some coordinate in CT. Okay, it sounds almost trivial because as long as CT has at least 1, 0 and at least 1, 1, it can output anything. Right? It just needs to, so it has to respond to this query. And we're just saying that its response has to be some bit in the actual query. And the only time that's not the case is if the query is all zeros or if the query is all ones. Okay, in that case, it actually has to output 0 in the first case and 1 in the second case. But otherwise, it can output anything it wants. But it only gets to see the values of the query restricted to the subset S. Okay, so this algorithm P only observes the query for the coordinates I and S. And so, if it sees all zeros in S, it better output all zeros because outside of S might be all zeros. If it sees all ones in S, it better output 1 because outside of S might be all ones. If it sees some mix of zeros and ones in S, it can output whatever it wants. Okay, you might think that this is a very weak requirement, but even with this weak requirement, you can show that there's a code that actually, an interactive code with a small number of queries that actually learns this set S. Okay, and this is useful in other cryptographic applications, watermarking, credit tracing schemes, and so on. See work of Bunei Shah. The result we use is of Steinke and Oben, which says there's an interactive fingerprinting code with order n squared queries, which actually breaks the algorithm. Okay, so yeah, let me go back. So intuitively, it's looking for correlations in the output. Okay, we know if the algorithm sees in its set S all ones, it has to output 1. If it sees all zeros, it has to output 0. And now you can think of what's going to happen if it sees something of Hamming weight 1. What's going to happen if it sees something of Hamming weight 2, and so on. And somewhere there has to be a jump. So it looks for correlations here, and that's how it builds its attack. Okay, I won't say the details, but it is non-trivial. Now this gap L0 norm problem, it needs to distinguish between the case where the number of non-zeros is at most alpha n, or at least beta n. So it's a stronger requirement than the fingerprinting code, which just needs to distinguish between all zeros and all ones. And so therefore, if your sketch, all it did was sample a set of coordinates, you can use this fingerprinting argument to break it for L0. I mean, for the number of distinct elements problem. Okay, but of course, sketches are much more general than just storing a subset of coordinates. How are we going to deal with general sketches? Okay, so let's revisit what we were talking about significant coordinates. So what we've said so far is that a coordinate I is significant if there exists an elementary vector, a standard unit vector EI, that's a row of the sketch. Okay, or in the row span of the sketch. But that doesn't quite capture this following upgrade to the previous example. So again, this input vector x is the same. The first row of A is the same as before. Now in the second row, what I have is some very large entries, say 999. Okay, and I look at A times x, and I look at the second coordinate of A times x, A2, and I see that it's 1,000. Okay, the fact that it's 1,000 actually indicates to me, if I knew that x were a binary vector, it actually completely reveals what that the second coordinate of x is actually a 1. Because if it were a 0, this number would be much smaller. Okay, so you see that you don't really need a standard unit vector. The sort of largeness of an entry relative to other entries in that row implies significance. And how do we formalize that? Well, the algorithm gets to sketch a times x, so it can recover the dot product of ax with any vector y of its choice in its post-processing. So y transpose ax. And what we're going to say regarding the definition of significance is the following. If there exists a y such that if I look at the ith coordinate of y transpose a squared, and this is at least a 1 over s fraction for some parameter s of the squared norm of y transpose a, then we're going to say that I is significant. Okay, so this is just capturing that intuition on the previous example. Okay, so we're saying that I can choose coordinates that contribute a large fraction of the 2 norm here. Okay, so you should think of S as being something like the actual sketch size. So maybe something like polylog n or so. Okay, so it's saying that I don't need to be a standard unit vector. Instead, I just need to contribute a 1 over s fraction of the norm of a row, for example. Okay, so that's what it would say if y transpose is just choosing a row. But in general, I can take any combination in the row span. Okay, so yeah, where are we now with significant coordinates? So I is significant if there's an elementary vector ei that is a row of A, or more generally, if there's some y such that y transpose A's ith coordinate is at least the 1 over s fraction of the squared norm of y transpose A. And you see that this more general condition implies this condition, right? If I just if I use y as ei, or sorry, I use y to select the corresponding row of A, then I get this with s equals 1, right? Okay, I mean, it is the whole norm of that row if it's a standard unit vector. Okay, so the second thing is more general than this first thing. But we're not done yet. There are other ways that a coordinate can be significant that are a little bit unique to this discrete setting that we're looking at in the streaming model. Let's look at the following. So suppose a row of A looks like this. It's 10, 10, 10, 10, 10, 10, 3. And I apply it to this vector x, 2, 3, 5, 0, 0, 1. Then when I take the dot product, I get 103. But actually, this entirely reveals what this last coordinate is. Right? Because, 2 times 10 plus 3 times 10 plus 5 times 10, that's going to be 100. Plus 3 times 1, I get 103. If I take this result mod 10, then it completely reveals what the last coordinate is. Okay, this has not, this coordinate is very small relative to the norm of this row. But nevertheless, it's important because it's different mod 10. So how can we capture this? So we need to further upgrade the definition of significance. And we say that you're significant if the fractional part, so again, you're ranging over all possible vectors y in post-processing. You can again think of this as just choosing a row of A if you like, some standard unit vector. You look at a row of A, and the fractional part of some coordinate is large, relative to the norm of the remaining fractional parts. Okay, so let me write that on the next slide. I is significant if there exists a y such that, now what frac means is, when I apply it to a vector, is take the fractional part entry-wise. Okay, so I just take the fractional part of every entry in the vector, and I look at the squared value of the I part, of the I fractional part, and it's at least a 1 over s fraction of the sum of squares of all the fractional parts. So this is our final definition of significance. So we started with this elementary vector, we generalize that to saying, there's an entry with large magnitude relative to the norm of what's left. We said that wasn't enough, so we said, if I take fractional parts, there's an entry which is large magnitude relative to the norm of fractional parts left. And in fact, this condition implies the other conditions, because the second condition I can scale down so that everything is fractional, for example. Okay, so, yeah. Okay, so we have our definition of significance. And what we're going to do is the following. So we're going to take our sketching matrix A, and we're going to pre-process it into a larger matrix A prime that separates out the significant coordinates under that definition of significant. Now this is only going to give the algorithm more information, so if the adversary can break this sketch, then it can also break the original sketch. So what do I mean by that? So here was an example A that we looked at earlier, a sketching matrix. We saw that this coordinate was significant, this 999. So what are we going to do? We're going to take this row here, this row, and we're going to split it into two rows. Okay, so we're going to pull the 999 down here. So we replace that entry with 0, and then we can replace this entry with a 1. Okay, so this sketching matrix from A prime times x, you can recover A times x. Okay, and this nice thing about A prime is, well, you can see that, now the significant coordinates, they are actually standard unit vectors here. And they're disjoint from what's left, this row. Okay, or they could be disjoint. I mean, I can subtract 1 from here. In general, the resulting matrix A prime after the preprocessing is going to have a sparse part, S, where all the entries are standard unit vectors, and a dense part, D, where there's no coordinate that's significant. Okay, so all the significant coordinates are going to be in the sparse part. Okay, that's the preprocessing that we would like. And the idea behind the attack is we want to reduce it to the fingerprinting code. Okay, so we're going to be making fingerprinting queries and trying to learn the sparse part. But the difference is there's a dense part. That's the difference from standard fingerprinting. But the distribution that we're going to apply in the fingerprinting code is going to be such that the dense part gives you essentially no information. And so it's as if we're running the fingerprinting code on only the sparse part. And so we're going to use correctness of fingerprinting to break the sparse part and therefore break the sketch.
But
Yeah.
The way you got the sparse row is like taking the significant coordinate and then making
Yeah.
the other 0. So, but they are mixed, right? Dense and sparse rows are.
So once you have a sparse part out, you can always make them disjoint because you can subtract the sparse part. But there is a question here is, as I'm creating this preprocessing, how do I know that it doesn't go on forever? Like maybe I'm introducing new significant coordinates as I'm doing the preprocessing, and then A prime is the entire maybe identity matrix, and then you can't break that. It's the identity matrix. It can store the whole input. So the sparse part S has at most one non-zero entry per column. Dense part D has no significant columns. And what we show is in this preprocessing, so the preprocessing is the really naive thing that would first come to mind. While there exists a significant coordinate, choose one of the significant coordinates, separate it out into the sparse part, and subtract it from the remaining part. That's it. While there exists, keep doing this, right? So this could, in theory, go on forever, but we show that actually it terminates after R times S log n rows have been added to A. Some notation, R was the original sketch size. S was this significance parameter. Remember that you're a 1 over S fraction of the norm of what's left. So we blow up the sketch size from R to R times S log n. S is going to be polynomial in R. Okay? So, we're still, as long as R didn't start too close to n, say is at most n to the point 1, this sketch will still be of size significantly less than n, and so it's breakable. So I can't really get into the details of why it terminates after this, but just to give you some intuition, it's an information theoretic argument. So if you were to choose a random x uniformly in -1, 1 to the n, then a times x only has order r log n bits of information, because a has r rows, each entry is a log n bit integer. But each significant coordinate, we can show it reveals about 1 over s bits of information of x, where 1 over s was this heaviness parameter. And intuitively, that's because this coordinate, when I take fractional parts, is a 1 over s, its squared value is a 1 over s fraction of the entire squared norm of fractional parts. And so there's an argument that if you were to subsample at a rate of 1 over s, with probably 1 over s, that coordinate would survive, everything else would be, the norm would go down by an s factor, and so that coordinate would be heavy, and you could tell if it's -1 or 1. So it's probably 1 over s, you can get 1 bit of information. And so what you can show is that each significant coordinate reveals 1 over s bits of information about x, and that's even conditioned on previous fixings of significant coordinates in previous iterations of the preprocessing. Okay, so I hope that's some glimpse of how this works, but it does terminate in rs log n rounds, and now we can use fingerprinting. Well, almost. If there were no dense part, we could use fingerprinting, but there might still be a dense part. And so, yeah, I only have a few minutes left. So the overall attack is we preprocess the matrix A into A prime that has a sparse part and a dense part. We use the fingerprinting attack on the sparse part, and we argue the dense part doesn't help. Why doesn't the dense part help? Okay, that's what we need to show. Intuitively, if I have just a sketch which is all a row of all ones, that doesn't seem very useful for estimating the number of distinct elements. If I take the dot product with some vector, it's a sum of many values, and it kind of loses, information about the number of distinct values. And that's why all known non-oblivious sketches, for L0 have a big sparse component to them. But how do we formally argue that for any sketch the dense part doesn't help? We design a family of distributions D over some domain where these are small valued integers, such that the probability that if I draw a sample x from this distribution at 0 is p. Okay, so I'm going to have a family of distributions parameterized by p, dp. P is going to range from alpha to beta in this gap norm problem. But the interesting thing that's going to happen is that for any different q and p, these are different probabilities of being 0, which is important because if I have n copies of this, the number of distinct elements is going to be pn or qn with high probability. The important property is we show that the image of the dense part of xp and the image in the dense part of xq are the same, okay, or they have small variation distance to each other. Okay, so that's how we formally say the dense part doesn't help. How do we show that these two images are the same? We need to carefully construct these distributions. Okay, okay, so let me just skip this since we're running out of time. So how do we construct distributions to argue the dense part looks the same under two different distributions that have a different number of non-zero typically have a different expected number of non-zero elements in a vector of length n. So we let p be the image distribution for one of these, dxp, and q be the image distribution in the other. And we bound the total variation distance between p and q. The way we do it is actually by a pointwise bound. The support size is not very large because these are the distributions of the images, so they only have rs log n rows after preprocessing. They're log n bit integers, so they're n to the order rs log n elements in the support of dxp and dxq. And so what we're going to show is that for every element in the support, you get a super close pointwise bound. And then you can just union bound over all the elements in the support to get your variation distance bound. I just want to say one thing to give you intuition about the preprocessing before I stop. To get this pointwise bound, so P and Q are these image distributions. You can use Fourier analysis to write it in a different form involving the Fourier coefficients of P and Q. You can use a triangle inequality to pull in the absolute value. Don't worry about that. The important point is when you write out the Fourier transform, what is the point of this fractional part? That's the only thing that's going on in the preprocessing. Why do we do that? Because when you write out the Fourier transform, we're going to choose symmetric distribution. So when you look at e to the minus I u dot z, where u is a Fourier coefficient and z is sampled from this image distribution, it's symmetric. So you get a cosine and a sine, but since it's symmetric, the sine part goes away. You take the cosine part and you expand it with a Taylor series. When you expand it with the Taylor series, it's cosine, so you're going to get a bunch of fractional stuff mod 2 pi. Okay? And the fact that we're able to first preprocess to make all the fractional parts small allows us to actually execute this argument to show that you get a small distance. That's one part. There's another part which is you need to show when you expand this Fourier coefficient, you get some even moments, and you need to choose your distributions carefully so that they match on the first number of moments, so that these Fourier coefficients are similar enough. But I just wanted to say where the fractional parts arise. They really arise when you're expanding e to the minus I u dot z into cosines, and the preprocessing allows us to bound these cosines. So I think I'm out of time. Is that right? 1 minute. Okay. Yeah. So you can bound the difference in Fourier coefficients you can write it out between the two distributions P and Q. You get one part that depends on the difference of their moments, which we choose the distributions carefully so they match. And you get one part that rapidly decays because of the preprocessing that we've done. So these distributions are constructed kind of carefully and cutely. So there's an elegant result of Larson, Weinstein, and Yu. If you want to look for ways of matching moments of distributions, look at that paper. There are some nice tools there that I don't have time to describe. So that's the overall attack that I said. The main result was that we can break any sketch with r to the 8th queries. We have additional results. So there are also algorithms that can estimate the number of distinct elements over finite fields. We can break any sketch over a finite field with a smaller number of r cubed queries. We have some results over the reals as well. Here it's the previous attack that used Gaussians in the work with Hart doesn't apply to L0, but we can get some results under some conditions for attacking L0 over the reals as well. There are a lot of nice questions here. So the attacks we have are for linear sketches. This is the last slide. So this is what we showed in this work. They can break L0 estimation. We actually have some recent work in submission that can break linear sketches for LP estimation on insertion and deletion streams now with finite bit complexity. These two results are for linear sketches. So there's a more general problem of a streaming algorithm, right? It's not necessarily the case that every streaming algorithm has to be a linear sketch, especially in the adversarially robust setting. So can you lift these to general streaming algorithms, and not just for L0, but also for LP? So that's all. Thanks.
Questions?
Yeah.
You mentioned that this gap is zero type analysis, like there are other problems. So what kind of problems?
Which other problems? Like.
So you mentioned that this gap is zero type analysis could be also one can use in. I mean, this is for distinct elements. Is it also useful?
Yeah. So what I talked about was all for distinct elements. In some recent work, we have it for LP norm estimation as well. You want to estimate the LP norm of an underlying vector. Is it at most alpha n or at least beta n? Yeah, I don't know what the general scope of this is. I think for you can rule out this attack I described with these Gaussian query vectors can rule out very large approximation factors, like even poly n approximation factors. So if you have some function which is poly n close within a poly n factor of some LP norm, you can also break those as well. But these recent results are just for constant factor inapproximability. So any function within a constant factor of LP can be broken with this. Yeah. Yeah.
How do you find y such that y transpose a square is dense in a coordinate or fractionally dense in a coordinate?
Oh, so we don't need to find it. So we say that a coordinate is significant if there exists a y, and the where is the definition? Yeah, we say a coordinate is significant if there exists a y, and note that the we're not assuming that the sketching algorithm is polynomial time or anything like that. So if there exists a y, then it can get some information by finding that y in whatever time it wants, and I can give it information about the coordinate. Yeah. Yes, this is a good question. If maybe some of these y's might be hard to find, and you impose some polynomial time conditions on your sketching algorithm. Yeah.
So let's thanks the speaker again. In the Department of Computer Science at Aarhus University. He has received his PhD from Technical University of Dortmund, and his research interest lies in online streaming, approximation, and learning algorithms.
Okay, so yeah, can you hear me? Does this work?
Yeah.
Good. So yeah, thank you all for coming, and yeah, thanks to the organizers for doing this. I had a blast. It was great. Please do it again. So this is joint work upcoming at the next SOTA with these four gentlemen here: Vincent, Andrew, my former student who is on the job market now, Matteo, and David. And yeah, for the most part of this talk, I would say I'm going to talk about why this is even an open problem. Robert Krautkammer was kind enough to explain this to me over, I don't know, I'm a bit thick, so it took me, I guess, half an hour. You guys get 15 minutes, but you're hopefully a little bit less thick than I was back then. So to understand what the open problem here even is, and then towards the end we'll get a little bit to the actual solution of it. So the problem that we're going to look at today is a clustering problem, K-median clustering specifically. So we're given points in some metric space. Say a little bit more about what type of metric space is later on, but for now just assume it's a metric space. And you want to find k-centers such that the sum of distances of every point to its closest center is minimized. Right, so you can ask to solve it, of course. That's not really what this talk is about. This talk is about how to compress it. Though you can use these things also within an algorithm that optimizes for the k-median objective. So the compression scheme that we're considering are core sets. What is a core set? So given that points at A, we're looking for a weighted subset omega. And the guarantee that omega, so these red points here are omega, the numbers above and below, those are the weights. You can consider maybe the weights as being something like a point represents this many other points, right? So is 4 means that this point corresponds to 4 others. And what we want the course set to satisfy is that the cost for any given solution is going to be well approximated. So if you take the cost on the original point set, you take the cost on the course set. In this case, for instance, this distance here would be multiplied by 4, this distance here would be multiplied by 2, and so on. You want those two costs to be fairly close. And the key property that course sets want to impose is that this guarantee holds for any given solution, right? So for all possible solutions that I could query, I want these two costs to be very similar. Okay. So, okay, maybe what I should say is, and we're interested in finding a course set that is as small as possible, right? So that's mainly what we're going to be about. Running time is also kind of important, I guess, but space-bound is going to be what I'm going to consider today. And just to give you like maybe one potential application, if your course set is just small enough, you can brute force it, right? So you can get like a 1 plus epsilon approximation, given that you can compute a course set fairly efficiently, and it's small enough, then you get a p-test or a fixed parameter, a parameterized p-test. As an immediate consequence. Okay, so what is a good candidate course set algorithm? For clustering, I would say all modern algorithms look a little bit like this. So you define some distribution from which you're going to sample points independently. I'm saying here it's not necessarily the uniform distribution, but actually for now I encourage you to think of it as the uniform distribution, just for the time being. And now you weigh the points. So in the uniform distribution, the points will be weighed by n over the course set size. And how do we analyze this algorithm? Well, we do this in 2 steps. First, we show that for an arbitrary but fixed solution, the cost is going to be well approximated. And then we're going to extend this to all possible solutions by enumerating over all of them. Okay, so those are the 2 steps that you have to take care of. There is some subtlety, like you can do better if you do not consider them as disjoint steps, but there's like some interplay that is going on. But I think to get like a first result, you just do these 2 steps. Okay, so if you are trying to get into course sets, there is some good news. That first step, the variance bound, that is essentially taken care of at this stage of course set research. So for all, I would say, useful algorithms that you might consider, we know what the variance is, or like we have a very good understanding of the variance, right? So you don't have to design a new, better estimator or worry about what, right? So you just find the corresponding lemma in literature, and then you just plug that into what you still have to do, and that is the second stage, which is, the union-bound stage. And this is kind of something that no real framework can ever take care of you to a complete degree. So if you're interested in some metric that no one has studied before, you're going to have to do some amount of work, right? So the first stage, that's good to go for now, and the union-bound stage, that's where we all still have to get creative. Now, generally, it's a good idea to just consider your metric very carefully and design like the best possible estimate as to how many solutions would exist. But suppose we don't want to do that. Suppose we do want some more abstract framework that takes care of many metrics to some degree. Okay, so how can we do that? We're now going to define a complexity notion on the metric. So I'm sure at least most of you will have heard of it at some point. It's called the VC dimension. And the VC dimension is now, it's a combinatorial notion, right? So the connection to clustering, that's not immediately given. So VC dimension is defined over range spaces. So I'm going to say, what is the range space that is relevant to us in this particular case? So the range space, I'm giving you a center C. Let's for now just imagine it's one center, right? And a candidate radius. And I'm now going to draw a ball of radius r around this center C, and I'm going to say you're contained in the range if your distance to the center is larger than r. So in this example here, this point is contained in the range, these two are not. So the two parameters that I have that I can use to get new ranges is C and R. So I can change R. In this case, this point right here enters the range, right? Or I can also move the center around. Okay. And for any range, you can now define the VC dimension, which is the size of the largest subset such that the power set is contained in the union of all of the ranges. Yes?
Complement of ball, like circles, now what are the ranges? Is complement of circles, the base?
No, I don't get it. But
Complement of discs, so you are saying that...
No. It's actually important that I don't say what is inside, but that you'll see in a moment why I need that it's at least R and not at most. But yeah, I guess the two ranges wouldn't be substantially different. So yeah, the VC dimension should only double at most. Right? Yeah. But you need these ranges for what I'm about to. And this is also what most people look at and study. Okay, so let's take a look at how these ranges could be helpful when it comes to designing courses. So if I have my uniform distribution where I'm saying, okay, all of the points are weighted by n over the course set size, this here is just now the estimator of the cost that the course set is inducing. If a mathematician doesn't really know what else to do, they just change the order of summation. So let's do that, right? So I can now write this in terms of an integral over all possible ranges of r, right? This is the same thing as this cost over here. Okay, so if you squint and stare at it long enough, that you can see that this is an identity. So this tells us that if I'm able to approximate these ranges very well, so let's for a moment not worry about how well I need to approximate them. So let's say we even have them exactly, right? If I had them exactly, then the cost would be perfectly estimated, and I just want you to maybe trust me that there exists like some approximation. If I can approximate or estimate the cardinality of all of these ranges sufficiently well, then I get a good estimate for this cost, right? So this is how this range space enters the picture, and the VC dimension it characterizes the richness of this range space. So how many samples do I need to take in order for all of these ranges to be well approximated? All right, so that's kind of like the overall idea behind this VC dimension-based analysis. Now, there is a problem here, namely that this identity here only works if the points are all weighted the same. If they're not weighted the same, right? So if I'm assigning a different weight for every point, then I'm stuck, right? I can just write that this cost looks like this, right? And I don't really know how to continue. And this is not just a technicality. So this is kind of where, in my thinking, I was stuck for quite a while. That I thought, like, how could it be any different, or just like view these weights as multiplicities or something? But it's really not that simple. So to kind of like contrast the difficulty by just considering this weighted range space, the difference lies in the fact that if I assign different weights to the points, what I need to show is that the VC dimension of this weighted range space is bounded. And it's really not that difficult to show that ranges that were not present previously are now present. Right? So these two range spaces are definitely not the same. And you cannot, it isn't known that you can just, as a black box way, say, okay, I take the unweighted range space and I work really hard and then I get a bound for the weighted. That doesn't work. Right? So those two things, in spite of looking very similar, are fundamentally different. Okay, so so the good news is that we do kind of have a fairly good understanding of the uniform range space or the unweighted range space, VC dimension bounds for various metrics, as we will see. But if you now just try to search the literature for weighted range spaces, you will not be able to draw upon so many results, right? So in this case, it's really not. I mean, because in some cases it really depends on what type of weights are you considering, what are the magnitude of the weights, and so on and so forth. Could the weights be negative? It's really not that obvious. And for your specific algorithm, like which weights will be relevant, that's like people weren't clairvoyant enough to kind of know which weights would be also relevant for you. So you can probably find something for the first type of range space, but usually not for the second. And we'll see two examples. Yes?
So why can't I just take R divided by WP as the radius and then I have the same range space?
So because that depends on P.
All R.
No, it depends on P.
Or the weight depends on P.
Right? This is like, that's why this, if I could do that, yes, I agree, but then I would be, this is essentially what a uniform thing is doing, right? That's why it doesn't work, yeah.
But is it possible to classify the points in some weight classes and then?
You can do that, and that blows up the number of, like the VC dimension. So this is, I guess that was an idea that, I think in a paper with David even, we did that, right? So you can discretize, but those things are almost never lossy. So if you're trying to now do something like, ooh, let's look very hard at what type of weights do I have and now bucket them or something, you're probably going to lose something, even if the analysis even can go through. Yes?
Do you assume any properties on WP? Weight function?
So right here I'm not. When you're now using it for a core set construction, you can assume certain properties, but this is kind of the difficulty. So it's still going to be on the core set designer to utilize these properties, because the people that may have studied this would not have been aware that those properties existed, right? So people that will have looked at this tend to not assume too much.
For example, if you assume semi-algebraic properties, you gain the VC dimension.
Yes, I agree. But so those properties for the strongest core set algorithms, they do not, like that doesn't hold. Yeah. Okay. So, so what can you do? Well, the solution, if you insist on just using the VC dimension so far, that people could come up with is insist that your core sets can only use uniform sampling as a subroutine. And you can make that work. Unfortunately, that is going to be lossy. So uniform sampling requires an additional computational overhead, or also space. Let's not worry about the computation time. It induces a space overhead, as we're going to see later where that exactly is coming from. And yeah, here is just like to give you some idea, like this. This log n, which we're typically really eager to avoid, right? If you want to brute force it, you don't want dependencies on log n. Yeah, this is kind of like the earliest type of reduction to uniform sampling that you could get. With a lot of effort, you could replace log n with dependencies on k and epsilon. Yeah?
What's the alternative notation?
Okay, like I'm adding polylog factors in k and whatever.
But not an
No, not an n.
N. Okay, thanks.
Okay, so up here, no, I think here you may have a log n, but down here you definitely don't, right? So I'm not, so it's O tilde only within the arguments that are inside of it. Okay. So, and now our result says, well, the uniform VC dimension is enough. You can get this core set bound right here, which is also the right answer. I'll say a little bit more about that later. And we also managed to use a non-uniform distribution to achieve this. So in spite of the fact that we're using a non-uniform distribution with all the difficulties that the weights induce, that is the way to go, and the uniform VC dimension is going to be enough. Okay. So since this is a geometry workshop, the two applications that I have are fairly geometric. So the first one is about clustering in minor free graphs. So the metric that you're looking at is the shortest path metric, and you're assuming that the graph excludes a fixed size minor. The most popularly known examples would be, I suppose, planar graphs, right? And the reason also why I like to mention these results is there's the alternative, of course, that you could always just try really hard, look at your metric, and obtain a result that way. So you don't have to go the way of VC dimension, right? So this is what these previous works up there did, right? This here was one of these more black box VC dimension-based approaches. But the previous work, they just tried to design something from scratch. And that turns out to I generally endorse that, right? Usually you should be smarter if you know enough about your problem than some abstract framework. But even then it turns out to be difficult to analyze this tightly, right? Yeah.
All the randomized conception, if it is deterministic, is there some lower bound now?
So for the most part, this is more about existence and information theory. Deterministic, you'd now be asking in terms of, like what is the running time that I would need, for instance, to de-randomize this stuff. And I don't think that there are many good deterministic algorithms for corsets in general. So the closest, so there are older results in Euclidean spaces, in low-dimensional Euclidean spaces that work. And you can also get a de-randomized version of a high-dimensional Euclidean space to some degree, right? So the running time is, it's FPT and K, so it's not that great. Randomization is generally the way to go. And one difficulty with designing deterministic algorithms is that it's not really known how to verify a corset. And that really is a fundamental issue. So randomized algorithm doesn't have to worry, right? It'll just be a corset with good probability. But a deterministic algorithm has to worry about that. Unless you have a very smart reason why, oh no, this will always guarantee to lead to a corset. But yeah, it's a difficult problem. Yeah.
Also that because the fact that VC dimension is bounded, then this is constructed by some net sampling, right? And
Yes, I'll get to the sampling distribution in a moment, yes.
And net we don't know how to construct it.
No. Yeah. I mean, you can de-randomize these nets, right? But the running time is always going to be exponential in K and the VC dimension, right? And even that de-randomization, that doesn't really work in a black box way, right? So even that is challenging. Okay, so the other example that I have, and this is, I guess, also work that Anna has been working on. I don't know, is this actually tight, the VC dimension? Do you know? Is this, like this thing up here, does there exist a lower bound? I'm not sure. Okay, you could cluster with respect, it is tight? Okay. So you can also cluster with a Fouché metric. In this case, your points are polygonal curves, right? And your center curve is now usually a somewhat simpler curve. And the VC dimension depends on parameters like the dimension of the space, the length of the curves, and so on. Yeah, and here you can also get better results. But a little bit more on that later. Okay. So maybe one final comment to kind of put this into slightly bigger context before I move on to how we did it. The bound that I gave to you today, that is tight, right? So if I'm not going to make any further assumptions on what the metric is, I cannot really do better than this VC dimension because there exists a metric where this corset size is going to be optimal. And the metric that satisfies this is a finite endpoint metric. Right? So in finite endpoint metrics, it's fairly easy to show that the VC dimension of the range space that I introduced earlier, that this is log n, and there's also matching lower bound. So you cannot do better than k log n times epsilon to the minus 2. However, I want to emphasize that the VC dimension is not going to give you an optimal bound in general, right? So that's also why I think it's probably better to, if you're really interested in your metric, to try to do something by hand. because in Euclidean spaces, the VC dimension is, well, to be very precise, it's going to be k log k times d, right? And we have core sets that are independent of d. Okay, good. So for the remainder of this talk, now I'm going to see how we manage to do this. And the starting point is going to be uniform sampling again. So we want to, like the uniform sampling already contains many key insights that you need to eventually get the right answer. So the reason why uniform sampling doesn't work is that it requires some amount of pre-processing. So if I just take this instance right here and take a uniform sample of it, I'm not going to see these 3 points, right? Unless I'm sampling close to n many points, I'm not going to see them. But they're important for the cost, right? So if I place this center right here, and I do not have these 3 points, then my cost estimation is going to be widely off. And so instead of just saying it doesn't work, you can actually say to which degree can you make it work, assuming certain additional properties of the data set. And it works if the cost is roughly of the order n times the diameter. So this is not satisfied here, right? Because the diameter, like whatever this distance here is, the cost is maybe 3 times the diameter, right? But if these 3 points wouldn't exist, then uniform sampling, at least you would believe that uniform sampling would work, because all of these points, they look kind of the same, right? So uniform sampling should do the trick. Okay, so what I'm going to show to you now is how you can actually use this theorem right here to get a first bound. And the person who did it was Chen, and would really say this is, if you want to get into core set research, read that paper, right? This is terrific paper, very approachable, far more approachable than everything that came afterwards. So the way that Chen does it is you compute some constant factor approximate solution. So don't worry about what constant. For now, let's even imagine I give you the optimum, whatever, right? So you compute a good solution, and now you partition your points into rings of exponentially increasing radii. So this is, of course, I hope that schematically it's clear what is going on, right? I know the rings are not it, but then there are not too many rings that I can fit on a slide if I were to do that. Okay, so you're partitioning the points by distance, right? And the distances, they increase exponentially by powers of 2. And now I'm considering one such ring, right, where all of the points are bucketed in between 2 successive powers of 2. And the reason why I did this is that now this, the number of points times the diameter of this divided by the contribution to their cost, this is now a constant, right? So this term right here that ruined my day for uniform sampling on the last slide, this is now a constant. So if you just look at this term right here, it just vanishes, right? So now uniform sampling works. And what I had to do in order to impose this is, well, pay with some pre-processing steps. So I need to now do this for every possible ring that I'm considering. And the number of rings that I have, well, it's like log n for every center, right? Because so you're starting at this value, and you can go at most up to the cost. So that's like log n many steps, since I'm increasing them exponentially. And I have to do this for every cluster of the optimal solution or the approximate solution. So that induces this k log n many rings. So the overall core set size, if you ignore polylog factors and so on, that's just going to be the correct bound, right, times a k log n. So what you could ask for now, there's basically 2 ways forward, right? You could first try to get rid of log n, or you could try to get rid of k. And we're going to get rid of log n first, and then also get rid of k in the final step. Okay. So so what we're going to do is consider not just every ring in isolation, but we have to group them in some way. And the way that the grouping works is that I'm now going to say, okay, all of the rings that cost the same, I'm going to put into the same group. Okay? So the rings here now, I'm saying like all of the rings cost the same, right? And within every ring, the points still have this property that they all cost the same. Okay. So yeah, and it's important to know like points in here and points there, they do not cost the same. So across different rings, they do not cost the same. It's just the rings that cost the same. So the number, and why am I doing this? So first off, it reduces the number of rings or the number of groups that I have to consider at the same time to polylog factors, if you do this carefully, right? So you don't have k log n in there anymore. You just have a very inexpensive polylog factor. So this doesn't solve my problem immediately, because I now have within every group k different weights, right? So I have, I basically have a weight here for these guys, a weight here for these guys, a weight here for this, right? And now there is actually somewhat good news in terms of the BC dimension, because if you only have k distinct weights, the BC dimension of the weighted range space can only blow up by a factor of k. So what you're going to get is the correct answer times the number of distinct weights in all of the groups. Okay? So this is already, like, it's already good progress, and I mean, this wasn't really what any of the previous work does. This is something that I was very happy to find out while preparing slides for this talk, that you can also do it a lot simpler. But yeah, okay, so you can actually use or like mitigate the impact that the weights do by just running this pre-processing step here. Okay, so yeah, what's left to do is now to get rid of this guy. Now, how do we do this? So this is just basically a copy of what we saw on the last slide. But I now need like one additional insight, one additional step in my pre-processing in order to get rid of this final k. So I'm going to group the rings such that every ring costs the same, and the ring radius is either equal or it is very far apart. So here, these two rings, right? They both have the same diameter, and this guy here doesn't, right? But I'm saying like, okay, here the radii of like if they're different, they have to be different by a huge gap. Okay. And so all the previous properties, they still hold. You have to pay a little bit in terms of the number of rings, but not too much. So the polylog blow up, that still holds, right? It's one log factor more that you're now going to pay. But essentially insignificant blow up if I want to impose this property. And okay, you still have k different weights in every group, but now something interesting happens. Namely that you can force rings where these radii are different to no longer interact. Basically, I'm saying if I'm placing a center close to this guy, if I'm placing centers so that I'm trying to kind of like break or induce many dichotomies for this, these cannot be relevant for those points, right? Without blowing up the cost significantly, right? Because this here operates in a very different cost regime, so I have to place centers further apart. And if I'm placing all these centers further apart, they cannot all be relevant. They cannot all be relevant for these points. So this property that the ring radii are far apart by epsilon factors, that really mitigates how many interactions can take place between the different clusters. So while I still have something like k different weights, I can now have a very tight control as to how good they interact. And if you now work very hard, you get the optimal corset bound. Okay, good. So let me conclude first with like some recap and then a few open problems. So first thing is that the VC dimension, despite being arguably the oldest or like the first abstract framework complexity notion that you would use to study corsets. It's also been open for the longest, right? And we've now closed this. And essentially for most of these abstract frameworks, so doubling dimension, VC dimension, we now have optimal corset bound. So it's really up to people that care about specific metrics to do better for that, right? So for abstract frameworks, I would say at this stage of corset research, we're as far as we can get. And what I also like is the pre-processing algorithm. So I'm pretty sure this has to have applications in other places, right? So this independence property, we used it just to bound the number of different interactions. I'm sure that it could probably also be useful in an actual algorithm rather than just for the sake of the analysis. And now let me leave you with two open problems. So the first thing I want to talk about are capacitated clustering objectives or fair clustering objectives. So one reason that we look at uniform sampling still to this day, it's the only technique that we have to deal with capacity constraints. And so our results do not hold for that, right? They only hold for, right? So we still have non-uniform distributions and those do not preserve mass exactly. So it would be very interesting, I think this is fairly challenging, but very interesting if you could get something like these bounds for capacitated clustering. Yeah, and then finally for the Frichet case, I've been harping a little bit about using abstract frameworks, right? And so we now recently managed to solve this, right? So you shouldn't use the VC dimension, right? And I know it's kind of like defeating the purpose of this talk, but yeah, if there's one takeaway, okay, you now know how to do it, but you shouldn't really. So you can actually do better if you do not look at properties of the VC dimension. And yeah, maybe there's also room for that for other problems. So I'd be fairly confident, for example, that you can do better even in planar graphs than the bounds that I gave to you today. Okay, that's it. Thanks.
Sensitivity sampling or like some kind of variant of sensitivity sampling, you do try first, or if you're sampling a variant of some type of sensitivity?
Okay, so what sensitivity sampling is, if you don't already know it, there's no way I can explain that, but there is, I would say that the corset algorithm that you want to use, that's what Arindam is alluding to, does it work for that too? And yes, it does. So the thing that we're giving to you here, you can always define the sensitivities as a mixture of the distribution that you're getting when looking at all of these groups, right? So you don't actually have to compute the groups. The existence of this is enough for you to also analyze sensitivity sampling with it, right?
You mentioned that there are some difficulties for designing algorithms that compute corsets, and such that the algorithms are deterministic.
Yeah.
Do you think there would be some chance to prove that there's some distinction between randomized and deterministic algorithms?
I really tried.
Okay.
Like separations of that sort, those are hard to come by, right? We don't know of a good deterministic algorithms for getting an epsilon net, right? So what I tried and haven't succeeded at showing so far is, let's assume that epsilon net computation in general cannot be done faster than something, that you can also not do faster for corset construction. But yeah, like epsilon net in general, it's a fairly general thing, right? And reducing that, like showing, okay, that corsets is essentially as rich as any epsilon net, that's a tall order, right? And I wouldn't really know. I mean, there's certain things in coding theory where you know that you have a randomized code but not a deterministic code, what you could base like a hardness conjecture on, but generally it's challenging, and if you have ideas, I'd be very happy to talk to you about it, but I tried for a long time. We got some results, and as miserable I feel as the results were, they were already very challenging to obtain. So like that you could get something that is FPT only in K and not in terms of the VC dimension, which also kind of suggests that the epsilon net thing is not a good conjecture to start with, right? Because in the Euclidean space, I can get it faster than what epsilon nets can get. Yeah. So, yeah. long story short, I don't know.
Thank you.
So let's thank the speaker again. So welcome back. So we have Professor Karthik CS. He is an assistant professor in the Department of Computer Science at Rutgers University. He received his PhD from Weizmann and he did postdoc at Tel Aviv and New York University. His research interest lies in complexity theory and discrete geometry.
Thank you. Thank you. So, thank you for inviting me to my hometown. And, so I'm going to go over clustering a bit, just to make sure we're all on the same page, although you've seen these definitions in the last few talks. So clustering is used when you have, for instance, these handwritten image data, and you can look at each image as a bunch of pixels, and then you can look at these pixels as some high-dimensional vector, and you want to sort of put high-dimensional vectors, two high-dimensional vectors in the same cluster if they are sort of close in some distance measure. I like abstracting, so let's abstract. You have some points in space, and I see clustering as just the task of classifying the input data based on some measures. Okay, so I want to model it, just so we're on the same page. So you have some metric space, so you have set gamma and some distance function delta, and your input is some subset of the metric space x, and you're given an integer k. And what you want to output is a classification, which is a pair. I can use this, which is a pair, and C and sigma, where C is just a subset of the metric space of size k. So these are your k centers, and sigma is a mapping of every input point to a center in C. So this would be a clustering, and you want sigma to be good, and there are various ways to model what is good. And this is what is called the continuous version, and it's important for this talk, this distinction, because I'm allowed to pick C anywhere in space, the centers anywhere in the space. But people also study the discrete version, where instead of picking anywhere in space, you're given a set of candidate centers as part of the input, and you can only pick your k centers from the set of input candidate centers. So this is the discrete version and the continuous version. These are the two versions in which clustering is typically studied. And there are many good objectives of what is good. K-means, K-median, K-center means some correlation clustering, hierarchical clustering, so many things. Of interest to this talk is K-median and K-means. In K-median, you want to find a classification which is minimizing the sum of distance of every input point to its closest center. And in K-means, sum of distance square instead of distances. So these are the two objectives we are interested in, clustering objectives. Good. So what is the computational question we are studying? We are studying the question of, you're given as input some input points, and you want to find a classification that approximately minimizes the clustering objective of interest. So we are going to deal with gap versions, because there's a hardness talk and it's easier to talk of gap versions. In the yes case, there is some clustering whose cost is at most beta. And in the no case, any clustering's cost is at least 1 plus delta times beta. Then we say if we show this is NP hard, then we have said that this NP hardness is shown for 1 plus delta approximation. Okay. So exact computation, we know that for the continuous version, even when k is 2, it's NP hard. Or if you're looking in the plane, Euclidean plane, in the Euclidean metric, then it's NP hard. So it's important to look at approximation algorithms because it's hard in these basic cases as well. Okay, these are a bunch of numbers. I want to say two things here. One, that this problem has been studied, approximating k-means and k-median clustering from the 80s or early 90s. And you can see that these are like recent line of works. So it's of interest to the approximation algorithmic community even now. So I have to revise this table every year, roughly. So it's still of very much interest. And the factors themselves, these are some numbers. it's not really important to know, is 9 good or 8 good or 7 good. It's more about what is the optimal value beyond which, below which it's NP hard and at which you can solve it in polynomial time. So really what matters is the truth and not really what this exact number is going to be. So this from the approximation algorithm sides. And in order to understand the truth from the other side, you need to prove hardness results. And in a bunch of works over the last 5 years with Vincent Koinada and Yung Lee, we have been sort of have these 3 papers and then there's some unpublished results. So this talk is mainly about sort of putting all of these together and giving you a coherent story as to what are the main takeaways from these set of papers, even the ones that are not published. And if anyone wants to read these things in more technical detail, I'm giving this talk as a commitment to write a journal version. So hopefully in a few months you'll have something to read. Good. So the state of art is this, and from now on, whenever I just say theorem, it's one of these papers. I don't bother citing which exact paper it is, because I've told you I'll write a journal version. Okay, good. So again, for the hardness factors, there are, in the discrete case, again, when the candidate centers are given to you as part of the input, we get a bunch of nice numbers. These are not like 1 plus epsilon, where epsilon is very tiny. These are non-negligible numbers. Some of these, the first 2 columns are under what is called JCH, the Johnson coverage hypothesis, which I'm going to tell later in the talk. And the other 2 are, we prove a weak version of Johnson coverage hypothesis, so we get unconditional NP hardness. So the numbers are a bit less here, but here they are more. And I'm looking at the general metric where you're just given the metric space as part of the input, L infinity, L1, L2. These are like some popular metrics to consider. In the continuous version where you can pick the centers anywhere in space, similarly, here there's a star mark. I'll get into this later. So these are numbers, but let me tell you, the things in red I believe to be tight. So in other words, it's the onus is on the algorithmic community to prove they're tight, because I don't think I can do better. And so I don't think you can beat these numbers. There are a couple of explanations for this. One is that if you relax your polytime algorithms to be FPT, then you get these numbers algorithmically. And the other is when you look at your linear program and you say the distances have to be 1, 2, 3, something like that, then you get these numbers. So it's more about how algorithmically you handle outliers while approximating and rounding and so on, which is a challenge, but it's an algorithmic challenge. The thing which I like here is this. I believe this is tight for L1, but it's under JCH. So proving JCH is a complexity theoretic task, so that I take up. Euclidean, I really have no idea what the right answers are supposed to be, so it's, we should work together. Okay, so again, these are some numbers. So this leads to 2 sort of sets of questions from a complexity side. How do you make progress on this JCH, which I haven't told you what it is, but I will tell you soon. But these are sort of like the motivating questions as to what I'm going to say next. And then how do you obtain optimal factors in continuous setting? Because even for L1, I'm not sure what to say here. And what the main message of this talk is, I'm going to present you with a very unified framework to sort of understand these things, make progress, and so on. Okay, good. Okay, so here is what I really like, is that clustering problem hardness usually comes from either set cover, vertex cover, these kinds of things, or more recently from coloring things. What I'm going to present to you is a new problem which involves matching. And a priori, it's completely unclear what matching has to do with clustering. But I'm going to show you that this will lead to tight results, or at least seemingly tight results. So here's a new problem involving matchings. and then the rest of the talk I'm going to give you proof sketches of how this connects to clustering. Okay, so if you haven't paid attention, just pay attention for this slide to just take away this problem. So the input is a graph, and the objective is to partition the graph, the vertex set of the graph into k parts, such that for each part you look at the maximum matching, and you want to minimize the sum of the maximum matching across the parts. Okay, and my claim is this is at the core of everything in k-means and k-median. No. So sorry. Yes. What is GI? GI is you look at VI and the induced subgraph of VI in G. Yeah, just that. So yeah, intuitively it's good to think of it like this.
So this is thing I don't understand. So this is just max matching is the number of edges only, right? Not in the matching. No weight.
No weight. Yeah.
Right. So then, so you are maximizing in each, and then
Minimizing the sum.
minimizing the. Oh, okay. I guess how do you make the k parts of the?
Yeah.
Right?
So ideally, what you would want to do is divide the graph vertex set into k parts, so that each part is an independent set.
Okay.
So if you k color the graph, you're done. Right? If you have k colored the graph, the max matching, max matching in any part is 0. When you sum it, it's 0. That's as low as you can go. And so the question is, how well can you approximate this thing? What's the worst thing you can do? Every part has full matching. So you have half in everything coming through. So n over 2 is like the upper bound and 0 is the lower bound. And I claim that, yeah, various special cases of this are what is needed for clustering. So this is a new problem and it's well motivated now. Okay. So let's see a full proof of how this gives some tight results. Good. So I want to say that there is a reduction which takes as input this k min-max matching problem and outputs a k-means or k-median instance where every vertex becomes a point. The number of coordinates is the number of edges, and we are in the L infinity metric space. I'm going to provide the reduction such that if the max matching sum is at most delta times V, then the k-means cost is 1/4 plus some order of delta. So I really think of delta as going to 0. So then basically the k-means cost is approaching 1/4 when you normalize, and k-median cost is approaching half in the yes case. In the no case, if you know that for every partitioning of the vertex set, the max matching, the cost, min-max matching cost is at least alpha times V, then I claim that the k-means cost is at least 1/4 plus 3 alpha over 2. So in the worst case, alpha is close to half, right? That's like if you do nothing. And if alpha is close to half, this k-means cost is approaching 1, and k-median cost is approaching 1 as well. So you get a 2 approximation hardness for k-median and 4 approximation hardness for k-means, which will give you the seemingly tight thing for L infinity space. Okay, so this is what I claim, and we'll see the proof now. So you're given a graph. The reduction is very simple, the point set itself. You orient the edges of the graph arbitrarily. And now for every point, you need to, for every vertex, you need to create a point. And the number of coordinates is just corresponding to the number of edges. So look at the vertex V, so the point PV corresponding to it. And you look at the eth coordinate corresponding to the edge E. It's +1 if E is an outgoing edge of V, -1 if E is an incoming edge of V, and 0 otherwise. So in other words, if V is of degree D, then you have D coordinates in which it's either +or -1 and then 0 everywhere else. Okay, what can we say about this? So if two vertices are adjacent, then their distance is 2 in the L infinity, because there is a coordinate E where one of them writes +1, the other writes -1, so the distance is 2. And if two vertices are non-adjacent, then on every coordinate, one of them is 0. So the distance is at most 1. Okay, good. Take an independent set, any independent set, and look at that set of points corresponding to that independent set. I claim that it has a center at distance half. Why? For every coordinate, and this is the center, I can write either plus half or minus half, because on every coordinate, exactly one of the points in that set has plus 1 or minus 1. Everything else will be 0. So I can just choose half on that coordinate with the corresponding sign. So every independent set admits a center at distance half. Good. So now let's just analyze what the clustering cost is. So take any subset of vertices S. Let's say its max matching cost is beta times S. And then I claim this. So let's go over this slowly. So what is the one median of the point set corresponding to set S? It's basically just, there is some optimal center CS, and then I sum over the distances for all points V, PV, V in S. Okay. Now I can partition this sum as to things belonging to the max matching and things not belonging to the max matching. If things belong to the max matching, so UV is an edge, so this is PU minus CS and PV minus CS. I apply triangle inequality, and I get that it's at least PU minus PV. And for the remaining, this is an independent set. If you're not part of the max matching, then you must be an independent set. And I know its distance is exact. There's a center at half distance. So I'll just choose. So whatever CS is, I just set this to be half. And I paid this much amount. So the number of points that are not in the max matching is 2 beta times S. 1 minus 2 beta times S. And for this, I know it's because things are adjacent, their distance is 2. So you get this quantity, 2 beta S plus half this thing. And in the upper bound, I just look at the independent set. I know there's an independent set of this size. I pay half. For the rest, I just pay the trivial bound. You're at most 3 half away from one of the centers. So you get this nice upper and lower bound. And the way to think of it is this. Your beta in the S case is close to 0. So this will be close to 0. And you're basically just S over 2 in the yes case. And in the no case, your beta is close to half. So the lower bound, here this S, and then this something. So in the no case, the cost is at least S, and in the yes case, it's at most S over 2. You get something similar for K means. The half is replaced by fourth because you're squaring, and so on. Okay. So all of this is good because what we have shown is that this is roughly true. I mean, that was the proof of what we just saw. But then we still need hardness for max matching. So there was this recent line of, the unique games conjecture, recent line of work, and then we got this very nice strong theorem from 2018 that given a graph, it's NP hard to distinguish if you can partition the vertex set into 4 equal parts, such that all of them are independent, or every independent set in the graph is of size at most epsilon times V. It's a very, very strong statement. So either the graph is almost 4 colorable, or it's at least you need a large constant number of colors. Okay. So from this, you can immediately conclude this by just taking the same instance and analyzing it. How do you analyze this? In the yes case, you have 4 independent sets. Good, you take them. You still have epsilon V amount of vertices you haven't accounted for. Each of them is in the matching. I don't care. It's just 2 epsilon V I pay. So it's some epsilon terms that I don't care about. In the no case, okay, so this is the nice thing. In the no case, if I partition it into 4 vertices, as long I look at, let's say V1, I collect epsilon V vertices. As long as I introduce another vertex, it's part of a matching. Every time I introduce another vertex, it's part of a matching. So you can show that V1 minus epsilon V over 2 matchings are there within V1. and similarly V2 and V3 and V4. So you get this half minus 2 epsilon. So you get this very strong separation. And from this, you just plug in the theorem we just proved now, and you get that k means is cost is, it's either n in the yes case, k means or k median, or in the no case, you get 4 here and 2 here. It's very strong bounds. And we are crucially using the fact that we are in the continuous space here. Because the choice can be, there are 2 to the n choices that we are exploiting here. This is, let me say that this is actually very counterintuitive, that continuous is harder than discrete. Because if you're an algorithm designer, and I tell you, oh, you have to pick centers from these input centers, you're more constrained in some sense than saying you can pick centers wherever you want. And still, we proved the other thing, that it's likely that the continuous hardness is much higher than the discrete one, because just the choices are too many if you're continuous to consider.
So that separation in the no case, that half minus 2 epsilon, so that sort of matters, right, of showing that this cost of this k means or k median is at least something. And this, how tight is that?
The epsilon can be made arbitrarily close to 0.
Sure, but that expression of half minus 2 epsilon. So
I don't think it matters, because you can just set epsilon as small as you want. Yeah, I mean, I'm abusing notation. There should be some epsilon prime and so on. Yeah. Okay, so this is L infinity, but let's try to abstract it, because I want to say something for the Euclidean metric. Yes.
Can we reduce the dimension? I mean, now it is like n-dimensional points.
Yeah. So we have a result in some paper, one of those things, where you say if you reduce the dimension, you can actually get a better algorithm.
Okay.
So it's like n dimensions, you need this.
Okay, so even like we cannot reduce by n to the epsilon or...
Yeah, n dimensions you need this much.
Okay.
But if you go to log n, you get a different hardness, which is closer to 3.94. It reduces to a discrete setting. When you're in low dimensional, you can convert the continuous to a discrete setting. I think, yeah, you guys can. It's all this core set business. Okay, let me go back actually, before I show you Pinocchio. Yeah, I want to abstract what we just saw as a reduction. So what we really want in the LP metric, is some one row C embedding, where if 2 vertices are adjacent, their distance is rho, or at least rho. 2 vertices are not adjacent, then their distance is 1. And every large independent set has a center at roughly distance C. Okay, I'm simplifying, I'm definitely lying, but let's take this as roughly what are the main ingredients that are needed to prove things in general. And then if you just run through the same proof as we did last time, you get something to this effect, that if the max matching is delta, then it's 1 plus delta times C square, and for the k means, and for k median it's roughly C. Here you get a quantity which depends on the hardness factor of max matching and the distance you can pull things apart if they are adjacent, rho. Okay, so you can abstract this whole thing, and I'm definitely lying, because there are more parameters that come in here, but this is like a simplified version to take away. And assuming this, let's try to show things for Euclidean k-means and Euclidean k-median. Okay, so I claim that assuming the unique games, so this is just a warm-up thing, this is not a final thing. Assuming unique games, you can look at vertex cover problem. From that you can deduce this statement. And I'm going to show how you get this from vertex cover problem. That given a graph which admits this 1 square root 2, 1 over square root 2 embedding, which means non-adjacent things are at distance 1, adjacent things are at distance square root 2, and there is a center for every independent set at distance 1 over square root 2. In Euclidean metric, it's hard to distinguish. In the yes case, the max matching cost is 0. And in the no case, it's at least 0.028 times V. So there's some separation between the two. Okay, if I have this, then I can plug in the theorem from the previous slide and get that k-means cost is either n or it's at least 1.056 times n. This is like roughly 19 over 18. So it's a non-trivial quantity. Okay. But what I want to really show is how do you get this version from vertex cover. And it's very clean. So let's start with this statement about vertex cover from Austrian code Safra, that in the yes case there's a vertex cover of size k, or in the no case every k vertices cover at most 0.944 times the number of edges. Okay. So vertex cover, in the yes case there's a vertex cover of size k, and I want to say that this translates to the problem of max matching in the following way. Okay. Let's suppose there's a vertex cover of size k. That means there are k vertices that cover all the edges. In other words, the edge set can be partitioned into k parts such that each part is a star. If the edge set can be partitioned into k parts such that each part is a star, in the line graph, these parts correspond to cliques. So a star becomes a clique when you take the line graph. So in the line graph, you can partition the vertex set into k parts such that each part is a clique. And if you look at its complement, then you can partition the vertex set into k parts such that each part is an independent set. And in the no case, it's a bit more trickier because suppose you can only cover some 0.95 fraction of edges, and you still look at the complement of the line graph. You will have an independent set, but you'll also have some edges there because you haven't covered everyone. And you can sort of pick out matchings from that and extract this number, which is basically 1 minus this over 2. So this is a bit non-trivial to see why the no case translates exactly tightly in the way it does. The idea is just if you have an independent set and then you have, it corresponds to a clique, right? So in the no case you can't partition completely into a clique. You'll have some other things here as well. So the things that are not there, you can pair them up with the other things to create the matchings. The main message is that this thing reduction goes through. Okay, now I want to say about the embedding. Because there's still graphs, but where does the embedding come from? The most naive embedding there is. You look at the original instance of vertex cover, and this is the embedding you create. In the original instance, suppose you had, so you're in the final max matching instance, a vertex is an edge, or is a non-edge here. So what you do is, when you start from the vertex cover instance, for every edge, if it's an edge between u1 and u2, then you create the point eu1 plus eu2. So you have n coordinates and you write 1 only on the coordinates corresponding to the two vertices of that edge. And I claim this is a 1 square root 2, 1 over square root 2 embedding. The reason is, if you take two edges and they are incident on a common vertex, their distance is square root 2 in the Euclidean metric. And if you take two edges and they are not incident on a common vertex, the distance is at least 2. So it's the most naive embedding you can think of, and it goes through the whole thing. Okay, so let me say a few words about the discrete thing very quickly. So the discrete thing has to do with min-max matching. It's just you're given m subsets of the vertex set V. There is no graph defined yet. And your objective is to pick k subsets out of these m subsets. And then the graph is defined based on what the k subsets you picked. So what you take is you take the clique and then you remove each of these subsets as independent sets from it. So in other words, this is like a choice of m independent subsets that you can remove from a complete graph. You pick any k of them, and that defines your graph G, which are the k independent sets you remove. And then you ask the same question: how can you partition now the whatever the graph left into k parts so that you minimize the max matching? And you can think of this as exactly coming from set cover, where every vertex is a universe element and every set is a collection of universe elements that are there, and a set covers something if it's an independent set, so you're removing all those edges out. So immediately you get, for this discrete version, a 0 versus 1 over 2e hardness. And the Johnson coverage hypothesis, I've talked about this in previous talks, but it's just saying the same thing holds even when the subgraph induced by the set system is subgraph of the Johnson graph. Or to go quickly, you're given a collection of t sets and you want to pick k t minus 1 sets so that you hit every t set in the input set. And in the no case, you can cover only alpha fraction of them. And we claim that the hardness still remains 1 minus 1 over e. Okay, and we can show some version of this is NP hard. And there are a lot of technical things to go through. Okay, so what are the key takeaways? One is that there's a new graph problem now. It's very well motivated and you can study it in all your favorite models and settings. Two, I still don't know if how to study these things in terms of embeddability. And three, Euclidean metric is very deep. I don't know what is the correct host graph to consider there. Okay, thank you. Questions? Yes. Yeah.
What happens if you want to minimize the maximum matching with constraint that you want to partition into k parts?
Yeah, so this should lead to some other kind of problem. It's like a minimization version of instead of this thing, right? Yeah, so this should have connections to facility location, for instance. Yeah. Yes.
For the lower bound, Euclidean norm, your lower bound holds for k equals to 4 even, right?
Yeah.
But for this Euclidean and all, do they also hold for k equals to 4 or like?
No, there are p-tasses
Oh, yeah.
for constant k.
But, okay. So, but for even A to infinity, we don't know anything for less than k equals to say 2 or something.
2 unique games hardness we know. 1 is easy.
Yeah, 1.
Okay, so let's thank the speaker again. He is a professor in the Department of Computer Science at IIT Delhi. He received his PhD from Cornell University, and his research interest lies in computational optimization approximation algorithms. He has received several awards, including Young Engineer Award from Indian National Academy of Engineering. He is also a recipient of Shanti Swarup Bhatnagar Prize for Science and Technology in Mathematical Sciences.
Thanks for the organizers for inviting me, and thanks for staying back till the last talk. So this is joint work with Anup Bhattacharya, who used to be a PhD student at IIT Delhi, but now is faculty at NICER, Bhubaneswar, and Ragesh Jaiswal, who is a faculty member at IIT Delhi. So the title of talk is FPT Approximation Algorithms for Constrained Clustering. So I'll explain what these terms are. But the previous speakers have done a great job of motivating k-means and k-median, and I'll also be working with these objectives. So, so this is the outline. So I'll briefly describe what k-means is, but I believe you've already seen these. And then we'll talk about some sampling-based algorithms for these problems, and then we'll go to what constrained k-means means. So at a high level, clustering problems seek to sort of, if you are given endpoints in some, think of this high dimensional Euclidean space. So D will be the number of dimensions, and I want to cluster them into k clusters. And so typically, so the left side could be the set of points, and then you want to, let's say, cluster them into 3 clusters like that. There are a lot of applications, as you have already seen: machine learning, data mining, vision, and many more. So I'll be focusing on a specific clustering problem. Perhaps the most widely used one. It's called the k-means clustering. So just to sort of reiterate, so the objective here is, so given a set of n points and a parameter k, my objective is to find k centers such that if you look at every other point and you measure its distance to the closest center, take the squares of all of those, add those up, that objective is minimized. So that's k means, right? And the points which are, every point is assigned to one of these center, and the points which are assigned to a specific center, they form a cluster. So essentially you're forming clusters of points. Other way of saying is that, if I give you these centers, then the partitioning is very easy. Every point just goes to the closest center. So it's just a Voronoi partition. And I'll just use one notation, which is given a set of points and a set of centers, cost of p comma c is essentially the k-means cost. So you look at every point, measure its distance to the closest center, take the square and add them. And we want to minimize that. So as the previous talk already talked about the hardness of this problem, it's NP hard even for k equals 2. And in fact, all exact algorithms take n to the d amount of time if we are in d dimensions. So we need fast and good heuristics. And so we are looking for algorithms which have small approximation ratio. And again, approximation ratio is, the definition is the cost of the algorithm by the optimal cost. So let's see what is known for even k equals 1, the most basic thing. So if you are doing k-means and k is equal to 1, it's easy to show that the optimal center is the mean of the set of points. So whatever the mean is, and the reason is that it's very simple. It says that if you look at any other point q and you measure the distance of all the points p to this q, the cost of that can be decomposed into cost of p to mu plus some term which is essentially proportional to the distance between mu and q square of that. So that's why if you want to minimize this, you're better off picking q as mu. So that just shows that mean is the optimal solution when k is equal to 1. So great. Now, let me sort of ask a slightly different question. What if instead of picking the mean, I pick a random point here? So I pick a uniformly random point from the set of input points. What is the cost? How bad is that? Again, it's not. So all you have to do is to take an expectation here where q is a randomly chosen point, and turns out that this quantity here is equal to this quantity here. So if you just do that calculation, so turns out that if I choose a random point q, the expected cost is just twice of cost of p comma mu. So that's great. So if you wanted a 2 approximation, you don't even have to compute the mean, you can just pick a random point. Now, what about k greater than 1? So far we have shown that a randomly chosen point is somewhat good. It gives a constant approximation. What happens if k is bigger than 1? Can I show that if I just choose randomly k points, that's good? For example, suppose k is 2 here. So does picking 2 random point give you a good solution? Yeah.
Random point from the set of points?
Yeah, from the input set of points. Yeah, so from the not the space, just thanks. Suppose so k is 2 here, and if I were to just choose 2 points, that won't be a good idea because maybe one of the clusters is very big, so both the points could be from here and would completely miss that other cluster. Right. So let's say if you choose 2 random points, they both happen to be here. The cost of that solution will be very large. And so the natural idea is to somehow not use uniform sampling, but somehow bias the sampling as you go on picking your centers. So this idea has been widely used. So the idea is follows that first center you pick. So you pick the centers in an iterative manner. So the first center is chosen uniformly at random. So let's say this one here. And the second one that you choose is now dependent on your choice of the first center. So the probability that you pick a point as your next center is proportional to the distance squared from this point. Okay, so now after picking, so then you're likely to pick somebody from there. And the third one that you will pick will again be proportional to the distance from these 2 centers that you've already chosen. Okay, square of that. So, so given a set of center C, the next point P is chosen as a center with probability proportional to its distance to C square of that. So this is called distance square sampling, and this was analyzed for the first time by a very nice paper by Arthur and Wasilewski in 2007, where they showed that if you're solving k-means for general metrics, it gives a log k approximation. More is known about this algorithm. If you are doing some sort of bi-criteria approximation, so if you want to violate the number of centers by a small constant, then, so for example, if you pick 2k such points, then it gives you a constant approximation. And in general, many practical implementations of k-means use this as a starting point. So if you're running Lloyd's algorithm, then this would be a starting point for picking the initial seed. In fact, we know that if certain conditions are satisfied, then this gives a very good solution. So, okay, but what we are looking for here is not just a constant approximation, but we want a p-test. P-test essentially means that I want a 1 plus epsilon approximation for any constant epsilon greater than 0. And we are looking for FPT kind of algorithm. So what that means is I will treat k as a constant. So I am looking for an algorithm which has running time of the form, let's say exponential in k and epsilon times polynomial in n and d. So I want a polynomial time approximation scheme which has this guarantee. Okay. All right. So so a lot is known here. So for example, there have been many papers which have, if you look at these running times, they're of the form that exponential in k and epsilon times some dependency on n and d. And Chris, I think, mentioned Chen's paper, so that uses core sets. So many of these papers rely on core sets. I will focus on one particular result, which again has running time 2 to the, there should be an order here, order k square by epsilon times d times n. Again, as you see, this is an FPT algorithm because running time is of that form. And the ideas here, we'll see that they extend to more general settings also. Okay, so let's go back to k equals 1. We showed that if you pick a random point q, it is a 2 approximation. But what if I want a better than 2 approximation? So a natural idea would be that you pick several points here, not just a random point, but let's say I pick a set of points s, and I output the mean of those set of points. Okay, so hopefully that would be a better approximation than just a 2 approximation. So what you can show, again, you can just do this calculation that if you pick s points, then your approximation depends on how big this s is. So this is a theorem which was noticed by Inaba, Kato, and Imai in 94, that if you pick about 2 by epsilon random points from the set of input points and output their mean, then its cost is at most 1 plus epsilon times the cost to the actual mean of the points. So you don't have to compute the mean of everything, you can just compute mean of roughly 1 by epsilon points. And that's 1 plus epsilon approximation. So already if you just are in k equals 1 case, this is enough. Okay, so how do you extend it to, let's say, more than one cluster? Okay, so let's say you are in 2 clusters, k is equal to 2, and you just want to extend this idea. Okay, so let's do the same thing. So the first sort of step would be that, so I'm going to assume that, so this is a technical assumption, but it's without loss of generality, that the k means cost, k is somehow the right number. So the k means cost is somewhat smaller than k minus 1 means cost. So for example, here the 2 means cost is somewhat smaller than the 1 means cost, at least an epsilon factor. Otherwise, why are you solving 2 means? You might as well solve 1 means. Okay, so so there is a separation between 2 means and 1 means. Okay, so so the algorithm is again the following. Let's say I sample some. So let's say this is a bigger cluster and this is a smaller cluster, and my goal is to figure out what mu1 and mu2 are. For example, earlier I was figuring out what mu1 was. Okay, so let's say I sample some, again, 1 over epsilon points, order 1 over epsilon points. I know that I will sample enough points from the bigger cluster. From the smaller one, I may not sample enough one, but from the bigger cluster, I will sample roughly 1 by epsilon points with high probability, with some constant probability, sorry. So, for example, here, these pink points are the sampled points. Now I will try all possible subset of these pink points, and hopefully one of them will be just a subset of O1, so I can take a mean of those, and that will give me a good approximation to mu1. Okay, so I try all subsets of size 1 by epsilon of these sampled points, and I can get a good approximation to mu1 prime. Okay, so so that's done. So that's great. Now what do I do? So again, I use the same idea as before, right? So now this is mu1 prime. So let us sample again lot of points, 1 by epsilon points, but now using distance square sampling with respect to mu1 prime. So you again sample points which are supposed to be far from mu1 prime. Okay, so you bias your sampling again, but again you sample a lot of points, not just one, but 1 by, let's say, epsilon square points. You will see why. Okay, so let's do that, and I want to claim that you will find enough points from the cluster O2. So it cannot be that even though this cluster could be very small, you will find enough points from there. Why? Well, the reason is that this is exactly what I assumed. I assumed that the cost of two means was much smaller than the cost of the one mean solution, which means that if I were to assign all of these points here, it will be very expensive.
It is sampling with replacement. It's sampling with replacement.
With replacement.
Same point can be selected.
With replacement. Yeah. So all of that was with replacement. Right. So the reason is that if all of these were to go to mu1, this will be more expensive than all of this going to what O1, all of O1 going to mu1. Okay. Because otherwise, this will one means will be as good as two means, which I assumed is not the case. So you do a simple calculation, and that shows that probability of sampling a point from O2 is at least an epsilon. So if you sample 1 by epsilon square points, you are likely to get 1 by epsilon points from this other cluster also. So again, I'll try all possible subset of T, and I am guaranteed that in one of those samples, I'll get enough number of points from O2. But there's one catch in this argument, which is that I wanted a uniform sample. Right? Remember that argument requires that you need to have uniform sampling from the data set to get a good approximation to the mean, whereas this is not uniform sampling. So even though you get enough points from O2, you do not get exact uniform sampling, but you can show that you get almost uniform sampling. Yeah.
So is it because you can have these repetitions can keep going if you do?
Also because the distance of everybody from mu1 is different, right? So everybody's probability is proportional to how far it is from mu1. Somebody could be close, somebody could be far.
Right. So this first step of d-square sampling, it's done with respect to mu1 or?
Right. So yeah. So this is with, I'm assuming that let's say you got mu1 exactly. Right?
You got mu1 exactly for mu1 prime, which is very close to mu1, and then how do you sample the next set of 1 by?
So everybody measures their distance to mu1.
Okay.
And then let's say distance are d1, d2, d3, and so on. So you look at d1 square by sum of everything. Right?
But when you are sampling the third point, will you include both?
To look at the closure of the two. Right? Okay. So far so good. Yeah. Yeah. So yeah, you sort of right. So what I want to claim is that when you sample from you do the sampling, so this is clear, right? You will have enough points from here, but they may not be uniform sampling, right? So some points could be sampled many times, or some points could not. I mean, the probabilities will not be same for everybody, right? And this is because the distances are different. But you can argue that I want to sort of sidestep this technical thing because most of the points are far away from mu1. So roughly they are equal, and you can do some justification that even though it's not uniform sampling, they're almost, they're not too far from each other. And then when I try all subsets, of that would be enough. So even though it's not true that their mean will be close to mean of O2, but when I try all possible subsets, one of those will work.
So are you recursing on all possible 1 by epsilon size subsets?
Yeah, so I'll show you the algorithm. Okay, so what we show is that this is a technical thing that there will be a subset of points from O2, 1 by epsilon points here, which will behave like a random sample. Okay, so this is the overall algorithm. So C is the set of centers you have chosen so far. So now you pick roughly, so that 1 over epsilon square becomes slightly bigger. Something like k over epsilon cube points using d square sampling with respect to the current set of centers that you have chosen. And for every subset of size 1 by epsilon of these 1 by epsilon cube points, you compute their mean. Okay, and then you recursively call. So each call will branch out into k over epsilon cube more calls. So at the leaves, you will have many solutions, and you will pick the best solution. Okay. So this algorithm, in fact, you can generalize to yield p-test for many other clustering problems, including k-median, can be implemented in parallel environment, And other faster p-TASes are known for this problem. This is not the fastest one, which uses this and combines this with core sets. So I won't get into those. But what I want to talk about was a slightly more general set of problems called constrained k-means. So
does it work for k-center as well, or?
not k-center, right? So k-means k. So okay, so constraint k-means is as follows. So again, same problem as before, but now I have additional conditions on what kind of clusters are allowed. For example, R gathering clustering says that each cluster must have at least R points. So we cannot have a cluster which has. So these are additional constraints one could add. Or another problem could be that each point has a color and each cluster has to be monochromatic. So that could be an additional constraint. Or what is called capacitated clustering, that there are upper bounds on the cluster size. So no cluster can be very big. Or what is called L diversity clustering, that each point has a color and no more than L fraction of points in a cluster have the same color. So you can imagine that there can be many additional constraints like these. And I'm just showing you some of these. And again, you want to solve k-means under these conditions. So what that means is that you want to, given a set of points p, you want to find centers C1 to Ck and a valid clustering. So a valid clustering is something which satisfies some additional properties. That's the kind of properties I showed you, such that again the objective, which is same as the k-means objective, is minimized. Okay, so you find clusters. For each cluster you find a center, and again it's the same objective as k-means objective, but now the definition of clusters is constrained. Not every partitioning of a set of points is a valid clustering. So so now what changes? What changes is that if I give you the centers, suppose I told you that these are the centers, it is no longer true that the clustering would be the Voronoi partition, because that may not be one of your valid clusterings. So you can ask, right, that so you can ask that suppose I give you the optimal centers, what is the corresponding clustering? So this would depend on on your actual problem formulation. Most of the time this will be some sort of flow problem. For example, suppose you are solving R gathering clustering. That is, you require that every cluster must have at least R points. So this you can set up as a max flow problem, because you can say that these are the set of points, these are the set of centers, and you want to assign every point to a center, but there are capacities on the edges here, right? So this becomes, so essentially you are trying to partition the points into 3 clusters where you are minimizing the cost. Cost could be on these edges, and every cluster must have size at least R. Right? So depending on what specific problem you are solving, there could be a different check function like that, which tells you whether a given clustering is valid or not. So this is something we'll assume that is given as a black box, and you can just call it to check whether a given clustering is valid or not. Okay? So far so good? Good. So what are the results? Ding and Zhou in 15 gave an FPT algorithm with this running time. We showed that the same principle or same ideas that I showed you, they give PTAS where you make so many calls to the check algorithm. So essentially this is you use this as a black box, but you make so many 2 to the k square by epsilon, those many calls to the black box algorithm. So I want to show you where why the same ideas would work even here as well. All right. So let's go back, right? So I showed you showed you an FPT PTAS. Where does it fail? Okay, and that will tell us how to modify that algorithm to take care of this case also. So what was the algorithm? The algorithm was that, let's say O1 is the bigger cluster, O2 is the smaller cluster. I want to estimate mu1 first. So what we were doing was that you sample some 1 by epsilon points, and out of these I know that I will get enough sample from O1, and you output its mean. So that idea still holds, because if you sample enough number of points, you will half of these, or roughly 1 by epsilon of these, will come from O1, and if you take their mean, that will give you a very good estimate of mu1, just exactly like before. So no change whatsoever. Okay. So so consider, suppose that you have got mu1. Okay. So that part still holds. Now you want to estimate mu2. So what was the algorithm? The algorithm was that you sample lot of points with respect to their distance from mu1, right? Points which are farther from mu1 are more likely to be sampled. So you sample them and then you hope that you will get enough of them from O2. Is that true? Yes. So the claim that we showed that you will find 1 by epsilon points from O2, that just relied on the fact that this thing held, and this we can assume again. So same thing will again hold. So same claim still holds, that you will get enough number of points from the cluster O2. But the claim which fails is that this will not be like a random sample. Why? Because this is no longer a Voronoi partition. So it is possible that there are a lot of points from the cluster O2 which are close to mu1, because we don't know how this partitioning happens. So given the means mu1 and mu2, you solve some flow problem to figure out what this optimal partitioning is. I have no idea how that looks like. So it's possible that a lot of points from O2 will be close to mu1. And so if you're sampling with respect to probability, which is how far away you are from mu1, it's not at all like uniform sampling. So these points will not get sampled at all. So there's no way you will get a good estimate of mu2. Okay. So for points which are far away from mu1, it behaves like random sampling, but for points of O2 which are close to mu1, it does not behave like random sampling. So the idea is the following. The idea is that if you have an estimate of mu1, I will just add some fake copies, fake samples which are close to mu1. So what I'll do is that I'll just add some copies of mu1 as proxies for points which are close to mu1. Okay, so this is what I will do. So I will sample some points using distance squared sampling, but in addition I'll just add some fake points here. Because I have no idea how many points are close to mu1. I'll just make a guess and add those many points there. Okay, and I'll just output that mean. So this is the complete algorithm. Right. So again, as before, you're given a set of centers C. When C becomes K, you're done. Otherwise, you sample roughly K by epsilon cube points using distance squared sampling. And for every center C, you add some copies of that as proxies to this sample here. And now you try all possible subsets, take its mean, and then again do exactly what you were doing earlier. Okay. So turns out that the black box algorithm check is only used at the very end. So you get a lot of solutions, and at the very end you check which is the best one. So the fact that you're solving constraint clustering is only sort of used at the very end. So it gives us a list of solutions, and I'm guaranteeing you that no matter which constraint clustering you're solving, one of them will be good. Okay, so in the last sort of maybe 5 minutes, I want to just show that we can even extend this to slightly more general settings, even when you have outliers. So presence of outliers can often skew your solution. So suppose you're solving k-means and there are 2 points which are very, very far away. So that could completely skew your solution. So what I want is now I want to even solve a slightly more general problem where you're given a set of points P and K, and M is an additional parameter. M says that I know that there are M outliers in my input, and what I want to do is I want to remove M points and solve the clustering problem on the remaining N minus M points. So I want to find a subset of size N minus M such that solving the constrained clustering problem on that subset, the objective is minimized. And I am treating both K and M as parameters. Okay, so the result we have is that again a black box reduction from the outlier version of this problem, so for this problem to the non-outlier version. So this reduction works for a large class of constraint clustering problems, as you will see. Okay. So let me just give you a brief high-level idea how this works. The main idea of the algorithm is that so this is what you have, right? So you're solving the outlier clustering problem. And the input are the set of points. X is the metric space, K, M, and check. And inside I will use as a black box the algorithm that I already showed you. So inside I will have an algorithm which will be the outlier free algorithm, which is supposed to cluster every set of points, or each point, sorry. And the algorithm is again very simple. All it will do is it will go through many iterations. In each iteration, it will somehow guess or figure out a set of points P0 to remove, and run the algorithm on the remaining set of points. Okay, and repeat this about k plus m raised to power m times. So remember, m is a parameter also here. So the running time will be of the form exponential in k and m times poly m. And how do I figure out this outlier set? How much time do you have? Okay, good. So how do I figure out this set of points p naught? So let's say that what I will do is I will solve a k plus m means problem. So k was the parameter k means and m is the number of outliers. So I will just solve the k plus m means algorithm, the vanilla one, without any constraints. I get a set of centers, and the outliers can be of two types. Either they are far from all of these, right? So they are completely far like this, or they are close to some of these. So it turns out that you can guess both of these by suitable sampling based ideas. So I will not get into those. But essentially the result we get is that suppose there is an alpha approximation for the constrained problem with running time tk, n. Then there is an alpha times 1 plus epsilon approximation algorithm for the corresponding outlier version. And the running time blows up by k plus m raised to power m kind of. And this generalizes host of these are all various clustering constraint clustering problems. So we get p-TAS for several new problems. For example, Euclidean capacited k means k median. This gives the first p-TAS for the outlier version, FPT p-TAS, sorry. So this is the last slide. So distance square based sampling techniques lead to FPT algorithms for many constrained and outlier constraint problems. Many of the non-FPT versions of these are open. So for example, getting a constant factor for capacitated k median is an open problem. So for many of those constrained clustering problems, it is open to get a non-FPT constant approximation algorithm. In the outlier version, we have m index as a parameter as well. So it's not clear if you really need that. So can you just get an FPT p-TAS which just depends on k only, not m as an additional parameter? So that's something we don't know. Thanks.